ladies and gents. Integration using partial fractions. So last week we went through revised partial fraction techniques. This week we're going to see how, having done that, that now means we can differentiate, integrate a function that prior to that we couldn't integrate. Right, here we go. So we looked at this function last week, the top there, and there's no standard entry in the table of integrals. However, last week we considered how we could rewrite or resolve that function into two separate partial fractions, as on the right hand side here. So how can we, using techniques we already know, integrate this function on the right? Well, what we can do is use our old friend integration by substitution that we learnt 2 weeks ago to integrate each part of a fraction, each fraction separately. So we'll go through that example now. How do we do integration by substitution on each of those functions? So if we go over this side and do the bit that is 2 over x minus 1, and we go over this side and do the bit that is 5 over x plus 3. What's the process for integration by substitution? We're going to do integration by substitution, and the first part of that on each side is to say let u equal x minus 1. Then what do we do with that? Integration by substitution. Du by dx. So we differentiate that function x minus 1. What do we get? One. And then what do we do? We need it in terms of dx because we want to use that to replace dx. So we say dx is equal to du. That is over 1. We don't write it, do we? Okay. We do the same thing on this side. So let u equals x plus 3. Du by dx is equal to 1 dx is equal to du. So carrying on this side, we can now say the integral of 2 over x minus 1 dx is equal to the integral of 2 over u du. So we replaced x minus 1 with u, and we've replaced dx with du. Yeah. Now if we integrate 2 over u, what do we get? Look in your tables. The entry you're looking at is the integral of 1 over a constant over the variable. So we could take that 2 outside, couldn't we? But it's going to be 2 ln u plus c. Yeah. And then we put back in what we called u, 2 ln x minus 1 plus c. So that's that side. Right, over this side, how do I carry this on? We're looking for the integral of 5 over x plus 3 dx is equal to integral of 5 over u du which is 5 ln u plus c. So which is 5 ln x plus 3 plus c. Yeah. Bringing that all together, we can now say that the integral of 2 over x minus 1 minus 5 over x plus 3 equals, that's going to be the integral of the first bit, and that's dx on the end there, equals 2 ln x minus 1 minus 5 ln x plus 3 with 1 constant on the end. You don't need the 2 plus c's can be brought together as 1 plus c. So you just deal with each partial fraction separately using integration by algebraic substitution, and then bring them all together at the end. No, you can't, because there isn't a common factor in those. It's fine. It is. Yeah. If you had 5 and 5, Callum, then yeah, you could take 5 outside brackets, couldn't you? If you had constants in front here and here that were both the same or had common multiples, you could take something outside brackets if you wanted to. No, sorry? No, ln is a function, isn't it? Natural logarithm of. Yeah? No, that's not multiplied by L times n. That's ln is the natural log. Yeah? Okay? So, what we got for you to have a go at is 3 examples of functions that require you, and I'll put them separately on the following pages so you've got plenty of room. Okay? So we got, the first one is 12 over x plus 3 times x minus 3 times x plus 3. So, solution first involves you resolving that into 2 partial fractions. So, from last week, we'll go through this one together. Where do we start? we've got 12 over x minus 3 times x plus 3. How do I turn that into two partial fractions? We have to say, no, we can't do that, can we? We say it's equivalent to, and that was a long while since last week, but I over one term plus b over the other term. You really have got to practice and remember these procedures, because there ain't no procedure on the formula sheet in the exam. I'll tell you that. Alright? Remember doing that? Yeah? What do we do next? Yeah, what effectively are you doing that, Cal? That's what you do, but what are you achieving there? What at the moment? What are these two fractions got? What's different about these two fractions than that one on the left hand side? They've got different denominators. So you multiply A by what's underneath B, and you've got to multiply B by what's underneath A. By doing that, you're returning to this common denominator. So we can go as equivalent to 8. If we multiply those two together, x minus 3 and x plus 3, we've got that. Yeah, and then those two can have the same denominator. So if we go I x plus 3 plus b x minus 3, we can now put that over the common denominator x minus 3 x plus 3. Remember that? Yeah. What does that then mean we can do? Well, because now this denominator and this denominator are the same, if they're the same, then 12 must be equal to this top line here. So we equate numerators. We say that 12 is equal to I x plus 3 plus b x minus 3. If the two denominators are equal, then the two numerators must also be equal to each other. Yeah? We've got two constants to find, I and b. What do we do? If we let x equal, first of all, 3, then let's say, if we let x equal 3, then here becomes 0, doesn't it? Yeah, that's right. Yeah. So therefore we can say 12 is equal to A times 3 plus 3 plus B times 0. So that term, I've included it for completeness to show what we're doing here. Making x equal to 3 means that we get rid of one of the known terms. So 12 is equal to 6a, therefore a is equal to 12 over 6 equals 2. So we've found a. Then, if we let x, as someone's already said, equal minus 3, that's going to make this term disappear. Yeah? And then, so we can say, therefore, 12 is equal to a times 0 plus 3 times minus 3 minus 3. 12 is equal to minus 6b. b equals 12 over minus 6 equal minus 2. Yep. So we got a is equal to 2 and b is equal to minus 2. We can put those values back into these two partial fractions. Yeah, and we're saying then that that function is equal to, that'll be 2 minus 2 on that side. Right, so I'm gonna yeah, I'm now going to, just let me get this first. So what we can do now, guys, is say that that is equivalent to a listening equivalent to 2 minus 2 that term, and now you can integrate that because you've got two separate fractions. Okay? So there's finishing that one off to get the complete integral, and there's two other examples for you to have a go at for the remainder of the session. I'm here to help. Practice makes perfect. Down there, Dan?